Hey everyone, welcome back to my daily coding series. Today's day 65 of Coding Every Day. I'm going to look at just another kind of problem that I'm going to pick somewhat randomly. So let's look at boats to save people. This is a 2-pointer question. So my goal for today, like I said yesterday, I'm going to stop using Paint, MS Paint, and I'm just going to do my problem solving on a document because that's closer to interview setting. I also want, going into this problem, to avoid overcomplicating things or trying to optimize too quickly. And another goal I have is focus on the general case first instead of edge cases. So that being said, let's look at this problem. Boats to save people. So we're given an array people, which is weights of every person, and an infinite number of boats, where each boat can carry a maximum weight of limit. Each boat carries at most 2 people at the same time, provided the sum of the weight of those people is at most limit. Okay, so we have boats, which carry between 0 and 2 people. But the weight, so the sum weight of those people must be less than or equal to the boat limit. So I'll say limit. So we're given, okay, and we want to return the minimum number of boats. We are given an infinite number of boats. Okay, return minimum number of boats to carry all people. So essentially we're given these weights and we have to break them up into groups of 2 or less so that we can carry them. And we get limit. So a way that I'm thinking about this logically is we want to get every boat as close to the limit as possible. So that way we can optimize and minimize the number of boats. So our goal should be get as close to the limit as we can. So here the limit is 5. So in this example, there are no 2 weights that will be able to be fit under 5. Now, my question is, what if we have a person who is a weight higher than the limit? Then that would be not possible. So this here addresses it. So every person's weight must be less than or equal to the limit. So it is impossible to have a weight higher than the limit. So earlier I said we want to get them as close to the limit. We definitely want to get them in groups of 2 if we can. And I think going towards the limit makes sense. So for instance, if we had an example with like 1, 4, 5. Let's say the limit was 9. And then we had 1, 2, maybe not 1, 2, maybe 1. Let's say this was like also 5. Okay. So in this case, you'd want to group the 4 and 5 together because it gets you closest to 9, and then you want to group the 1 and 5. So the correct answer would be one boat would be 1 and 5, and another would be 4 and 5. So you can't just group. So for instance, if you said 1 and 4, that would be incorrect because you can't fit 5 and 5 together. So we can't just do groups of 2. The way that we arrange the people does matter, as shown by this illustration, because you would need So we can't just group the people in whatever grouping. Yeah. And if we get it as close to the limit as we can, then that would yield the minimum number. So what I'm going to say is by getting each boat as close as possible to limit, we will minimize number of boats. And I think that is probably always true. So I'm just going to operate under this assumption for now. So let me think of an algorithm on how we can get each boat as close as possible to the limit. Yeah. So I'm also thinking you may be interested in sorting the people's weight. And I think that would give you a lot of utility. So maybe it's not necessary, but for now, I'm going to do a sort approach. So let's look at, for instance, 1, 2, 2, and 3. So this is after we sort example 2, and the limit equals 3. So what I would do is probably start with the heaviest person, and see, can we fit so here the remaining would be 0. So I can think of an n log n approach where, so we have okay, so let's say that in this example the limit was 9, or I don't know, I'm gonna just make imaginary longer. Let's say our limit was 20. Okay, so what I would do is take 15, and then I would, so then our remainder here for this number would be 5. So we'd say remainder equals 5. And then I would binary search the rest until we get the largest, the element that is as close to 5 as possible, and then group it with 15. So in this case, we'd get 15, 5. And then, so we'd have to somehow like pop this from the list, which would be n. But then we would look at 10. We'd say, okay, 10. The remainder is 10, so then we would get 6 together, right? So this kind of pairing would give us something useful. So this idea of like trying to get the best pair possible, so maybe you could start, it also might be a fair assumption to make that, so if we have just 2 pointers at each end, right? So if we had like I and J, it would be fair to say that, okay, if we can fit both of these, then we should. So let's say the limit was 20. We would want to pair the heaviest and the smallest together, because we know that there will never be another J, which we would need something smaller than I. And if it can't fit the limit, so maybe it's just that is the approach. So if we can't fit the limit, so let's say the limit here was 12, then we would put J in a boat by itself. And then we would say just 15, because this is greater than the limit, and then we'll move J over. And then we'll say, okay, j has a remainder of 2. So we'd say here at j right now, the remainder is 2. I is less than 2, so we should just add them together. And I think this would work because, like I said earlier, no matter which j we get, we'll never need, there's never a better case to use this 1 because this is the heaviest that we have available. So, and then we would just keep going until we fill out all our boats. And for the sake of this problem, I don't think we need to output the boats themselves. So we wouldn't have to store this. We could just have a single variable. So this approach would take n log n to sort, and then this would be linear because we're just moving I and j. So this approach would be n log n. So I think what I will do, I mean, that sounds good. I think what I'll do is, I don't want to optimize too early. That was one of my goals for today. So I'm going to try coding this algorithm. So let me just walk through a couple examples with this algorithm here. So in the first example, we have 1, 2 with a limit equals 3. So we'll have our pointers I and j. So we'll look at j, and we'll see that the remainder is 1. So we can fit I and j into the same boat. And then we'll move j minus 1 and I plus 1, and then we'll stop because now I is greater than j. That'll be our stop condition. And our boat there would be 1. If we look at another example, 1, 2, 2, 3, where limit equals 3, we'd have I and j like so. So this boat can't fit anymore. So like j is greater than or equal to the limit. Well, I guess I plus j is greater than the limit. So we would, because we know j has to be less than the limit. So we're checking, is I plus j, so is I plus j greater than the limit? If it is, then we just add j. So just add j, otherwise, so this is kind of like a ternary notation here, versus add I and j to same boat. Okay, so we see that here, they're over the limit, so we're just going to add 3 as a boat by itself. And then j, of course, will get incremented there. And then we'll say, okay, they are equal to the limit, which falls under less than or equal to the limit. So we'll add them to a boat together and move both of them. And then, so this is kind of like an edge case, like when I equals j, we don't really want to add them together because that would give us 4. So we may want to say, we may need to put like if I guess I could do it over here. So if I equals j, then just add like a of I to a boat. And then, you know, or we could just increase the boat counter by 1, because if I ever equals j, then that means there's only one number left that we haven't added, so we just add it. Okay, so that's the gist of it. And then, yeah, so let's start to do this here. So we'll say people.sort, that's the first step. That's n log n. We're looking at 15 minutes, so this looks good. Okay, now we're going to say while I is less than or equal to j. And then we'll set, of course, I equal to 0 and j equal to length of people minus 1. So those are both our pointers. So now we're going to ask that question. Is I plus j greater than limit? So if people of I plus people of j is greater than the limit. So in this case, this means we only add j. So we'd say so that the count would go, so we'll have the number of boats, I'll just put it here, so number of boats would go up by 1, and then j would go minus 1. We only move j. So I'm going to reverse the logic on this. So j will move no matter what, but only sometimes I will move. So I'm going to say if, okay, I'm optimizing a little too early here, but hopefully it doesn't bite me. So if we can fit both of them, then num boats will go up by 1 and I will go up by 1. And then no matter what, j goes down by 1. So I'm optimizing too early here, but I think this makes sense. So if it's less than or equal to the limit, we can fit both of them. So then we're just going to move both the pointers in. And now the only case, so yeah, I'll have it like that. And then if I equals j, then we'll just say num boats plus equals 1 more after we exit the while loop. If they're not equal, then we don't add an extra boat, and then we can return num boats like so. We need a limit. Yeah, I use it here. J will always go down no matter what. Okay, let's try running it and see if it works for the test cases. We're at 16 minutes. Okay, we have some wrong answers. So let me print, because I already went through this example, so that means it's a code error. So let me print here what I and j are and see if it's what it should be. So I and j are 1 and 1. So in this case, we'd have I and j here, just j moves up. Let me say here, put people I and people j into a boat. Oh, we need an else statement. No? Let me say else. So otherwise, we just put people j into a boat, and then this j will go no matter what. So let me see if this is inconsistent. So we put 3 into a boat, we put 1 and 2 into a boat. Maybe num boats should always go up by 1. Yeah, that was probably the logical error. So num boats should always go up by 1, because even if we just add j to itself, it should go up. So then we can delete. Well, first let me submit and see if this works. Okay, so that does work. So let me delete these print statements here. Like this, and then keep that. Okay, so it looks like there might be something faster than nlogn. Okay, maybe not actually. Well, it seems like I'm in the right sort of area. Yeah, okay. So it looks like I did it. I think nlogn is good. Okay, great. I think that went well. I'm happy that I talked it through, and then I went for the nlogn approach instead of overthinking it at the beginning. That's good. I made assumptions and just went with them. And if they ended up being wrong, I could have went back. But yeah, I'm pretty happy with that. So I'll call it for the episode. So thank you guys for watching. 20 minutes. That's like a really great time. That was another goal of mine, is I wanted to try to be a bit faster and take a bit more risks. So I'm happy I paid off. So thank you guys for watching. Today was day 65, and I'll see everybody tomorrow for day 66. Goodbye.